Hello and welcome to the second of the lectures in this week 12 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the previous lecture, we had questioned ourselves if it were possible to extract the properties that led to the desirable properties of a fuzzy inference system. If you were able to extract those properties as functional equations or functional inequalities, and if we knew that there are also implications from outside of the family of R implications which satisfied them, can we really employ those implications also in an FRI or an SPR? And if we do they also enjoy the same desirable properties that we expect from an inference scheme, that of monotonicity or interpolativity, continuity or robustness? In this today's lecture, we will discuss the suitability of Bangalore cohort subproduct inference scheme, but with a difference. We will use one of the Yager's families of implications, either an F implication or G implication, in the place of a residual implication obtained from a left continuous T-norm. Let's have a quick recap of the mechanism of fuzzy relational inference. We are given a seesaw rule base, a single input, single output rule base, n of them, such rules. What we do is we relate the antecedents and consequence by a fuzzy relation. So for each rule, we have a relation Ra. Now, we know these are the commonly employed relations, R check and R cap, where with R check you use a T-norm, and in case of R cap we use an implication. Now, given an input A dash, we obtain the output using a composition operator, and of course we use, in the case of multiple rules, either the theta or the Fati inference strategy, which essentially means if it is Fati, what we do is we aggregate all the rules, the relations of the rules Ri, using the aggregation function G, and then compose the given A dash with the aggregated rules, or we compose A dash with each of the rules, the relations of the rules, and then finally aggregate them. So this is how we obtain the B dash. The typical compositions are the sup-T and the inphi composition. So these two are packaged together under FRIs, and one of them, when we use sup-T composition, we call it the compositional rule of inference, and in the case of BKS inference, we use the inphi composition. Now, what do we want to do? We want to take a fuzzy relational inference scheme, look at it as only a mapping between f of x to f of y. In that sense, for a given input fuzzy set A, this inference scheme depends only on R, the relation, and the composition map. So if you consider this either the sup-T composition or the inphi composition, this is what we call the CRI or BKS. We know that for R, both R check and R cap, they play an important role, either in terms of the corresponding interpolativity of the corresponding FRIs, or theta being equal to Fati, or being able to look at FRI in terms of SPR. But now what we want to do is we want to generalize this, at least since we are using an implication. Let's generalize the Bangalore cohort subproduct, wherein we are considered using a residual implication. Instead, now we will use an F implication. Of course, since it is only inphi composition, instead of using IT, we could use an IF. But the question is mere substitution enough? As a composition, it may be okay, but now what we are looking at is as an inference scheme. So as an inference scheme, we know that we expect a few desirable properties of an inference scheme. Some of them that we have discussed over the last 4 weeks are these: interpolativity, continuity, robustness, and monotonicity. So instead of merely substituting and saying let's use it, we should also, after substitution, discuss these properties. And that's what we will do in the rest of this lecture. So we'll denote the Bangalore cohort subproduct inference scheme with F implication by using the symbol delta F. So it's an inf-IF composition where IF is the F generated implication. Similarly, we can also discuss the inf-IG composition where IG is the G generated implication. We will see from the approach that we take in this lecture that we will discuss BKSF in depth, but it is clear to see as we progress that whatever properties that we discuss with respect to F implications, if you substitute a G implication in its place, the same properties will also hold. Let's recall the definitions of these two families of fuzzy implications. The F implications, which we will denote by F, these are obtained from the additive generators of T norms. That means these are functions from 0, 1 to 0 infinity, which are strictly decreasing, continuous with f of 1 is 0. And this is the formula of an F implication, F inverse of x into f of y, with this convention. Similarly, for G generated implication or G implication, it is obtained from the additive generators of T conorms. Means G is a function from 0, 1 to 0 infinity, which is strictly increasing and continuous, with G of 0 is 0, and the G implication itself is given by this formula. Note that we also employ this convention. What are the properties of Yager's class of fuzzy implications? We know both of them are neutral. We will indicate it for the F implication, but many of these immediately follow also for the G generated implications. We know clearly it has neutrality property. In the previous lecture, we have seen that F and G implication, they do satisfy law of importation with respect to the product T norm. And we have seen that any implication, as long as the index set is finite, also satisfies both these distributivity laws, the antecedent distributivity and the consequent distributivity. And as was mentioned, these are properties satisfied by G-generated implications also. We'll introduce what are called generalized Gaussian implication. So this is a function from 0 infinity square to 0, 1. Why is it called generalized Gaussian implication? Because it generalizes the formula of Gaussian implication, which is the original Gaussian implication we have seen is from 0, 1 square to 0, 1. And here, essentially, we take the same formula, but only that we allow the x and y to vary from 0 infinity. And of course, with this convention. Now, once you have an implication, you also can get a by implication, which is typically x by implication y is x implies y and y implies x, where and is interpreted as the minimum operation. And you see that these are actually, while x and y are coming from 0 infinity, we know that the corresponding x implies y with respect to this Gaussian implication, generalized Gaussian implication. They actually push it to the 0, 1 interval. So it's essentially min operating on values in 0, 1. Of course, we use this convention. Now, if you take this generalized Gaussian implication and its corresponding by implication, if you pick these points a, b and ai's and bi's from 0 infinity, once again where I comes from a script I, which is a finite index set, and if you consider the generalized Gaussian by implication, we can show the following properties are in fact true. Please recall the second of the properties is something that we have made use of many times over. Here we are using the Gaussian by implication and the product T norm, whereas when we discussed from the residual lattice structure, these were the by implications obtained from the R implication, the residual implication, and instead of product we were using the star, the T norm that gave rise to the residual lattice structure. Now let's begin by discussing one of the desirable properties, and slowly we'll move on to the others also. The first of them, as we have seen, is interpolativity. So note that by interpolativity we only mean that if the input matches one of the antecedents, then the corresponding output should be the corresponding consequent. Now we are looking at FRI as a mapping from f of x to f of y, where R is some relation and we have a composition, some composition at the end. So in that sense, we are going to use delta f, that is BKSF, which is BKS with f implication for the implication in the composition. And we are now looking for an R. That's the generalized perspective that we have had for quite some time now. Now we have seen interpolativity is also related to solvability. So we're questioning, okay, when is A composed with R equal to B? Then A is A and B is BI. Can R be any fuzzy relation? We have seen in the case of sup T and inf IT compositions, R cap and R check played a very major role. However, we also knew that we could consider any R which was giving us interpolativity, and such relations are, we call them correct models. So now the question is, for this BKSF inference, what is the correct model of R? That is, can we find an R such that AI BKSF composed with R is actually equal to BA for every I? Now, what could be a possible relation for R? Now, taking Q from R cap, because we are using an implication, why not consider this? So instead of using an R implication, why not use an F implication is the question. Well, let's go ahead and use this R of cap as the possible relation. We have a result which says that if the antecedents are all normal, then the following are equivalent. This R of cap is a correct model of the rule base for BKSF composition. What does it mean? That means using this R of cap, we can ensure interpolativity. This is true if and only if for any ij coming from 1 to n, the following inequality is in fact valid, where the by implication is the generalized Gaussian by implication, and the F that we have here, it is not simply just the output, the consequent fuzzy set of the rules, but F of that, so transformed by F. So this is the result that we have. So R of cap can be considered as an admissible relation. It will have interpolativity, it will give rise to interpolativity in a BKSF composition, provided this inequality is valid. Now, it's quite eerily similar to what we have seen earlier. Remember, when we are discussing Supti composition with R cap, we have seen this result by Plavon, which says that if A is normal and if this inequality, what we called as the semi-partition inequality, if it is satisfied, then we know that that corresponding R is in fact an admissible relation in the inference scheme. Of course, the by implication there was obtained from the corresponding R implication. In our case here, what we see is almost the same thing. We are obtaining the by implication from the Gaussian implication, the extended Gaussian implication, and instead of using an R implication, we are using the F implication here. And we have ensured under this condition that the system will be interpolated. Now, what about continuity? Well, what is continuity? We have a relation R. We say it is continuous model for the rule base that with respect to this composition, if for each I, the following inequality is valid. Now, why is this continuity? We know that the by implication can also be looked at as an equality, equivalence relation with respect to a particular T-norm. So in that sense, the right hand side, it reflects how close the inputs are to the antecedent, and the left hand side reflects the closeness of the output to the consequent. So essentially this is what it is trying to capture. However, we can also give another interpretation. Recall that when we talked about having psi tilde, which is the system function of an FIS seen as a mapping from fx to fy, we called it a continuous model for a given rule base if and only if this property was valid, and we were able to show this actually related to showing that we created a metric TF on the input and output spaces, and we showed it as the corresponding outputs from the inference obtained for a given A. We showed that as a mapping with these metrics on fx and fy, they can be considered continuous. In fact, a similar kind of result can be shown when we are using BKSF. This equation that we saw a couple of slides earlier, we called it the continuity equation. We can show that psi tilde, which is a system function obtained from BKSF for a given rule base, it is a continuous model if and only if this is valid, this inequality is valid. And why is this called continuity? Because we can construct metrics on y, f of y and f of x, dy and dx, such that once again, as inputs are closer to antecedents, we can show with respect to another metric, the corresponding outputs are also closer to the consequence. So that is why we could consider this inequality as an equation of continuity and say the corresponding model is continuous. Now the question is R of cap continuous? Does it satisfy this inequality? Only then we can say that yes, the corresponding system function is continuous. Well, let's start with the CISO rule base. we can show the following are equivalent. That means RF cap is a continuous model for the BKSF inference in a given rule base, if and only if it is a correct model for this. So that means the equation of continuity and the earlier equation that we insisted for interpolativity, they must be really equivalent. That means one should imply the other under the condition that we are considering for R cap F. So this is the condition that we thought of. Inequality we call it as equation of continuity. So what it means is, if you have continuity, correctness is nothing but interpolativity. So we have also found the conditions, almost the similar conditions for F for you when you employ F implications in BKS to ensure both interpolativity and continuity. And as in the case with R implication, we have shown that these are in fact equivalent. If it is a continuous model, it's a correct model. And if it's a correct model that is interpolative, then it is also continuous. Now, what about robustness? Let's recall what is robustness. It deals with how errors in the premises affect the conclusions. It is different from continuity. In words, what does it say? It says that when the actual input is not exactly the intended fuzzy set, maybe close enough based on the way we have captured the fuzzy set, even if it is not exactly the same but close to the intent set, but somehow is equivalent in a certain defined sense. So there is an equality relation between the output of the actual fuzzy set is also close to the intended output. Towards this end, we introduced the concept of extensionality. So we began with an E, which is an equivalence relation, fuzzy equivalence relation with respect to a given T norm star. And if we take a fuzzy set A on X, we define what is when this A is said to be extensional with respect to this equivalence relation as follows: that A of X star E of XY is less than or equal to A of Y for every XY in X. And given an A, even if it is not extensional, we can make it extensional by constructing the extensional hull of A with respect to E star. This is the formula that we have seen. It essentially means A cap is nothing but the smallest extensional fuzzy set of A containing A. The smallest extensional fuzzy set with respect to E that also contains A. And of course here we are using the pointwise ordering between the fuzzy sets A and C. Well, what is robustness? You could put it simply like this: given A dash as the fuzzy input and an R, we say an FRI is robust if A dash composed with R is the same as composing the extensional hull of A dash with R. Well, it is clear that robustness of an FRI depends on fuzzy relation R and the antecedence A of the given rule base, because we have fixed the composition. Once again, it can be shown that if you take a fuzzy equivalence relation with respect to the product and let the seesaw rule base be such that every antecedent A is extensional with respect to E, and this dot represents the product and if you model the R using RF cap, same RF cap, then it can be shown that for any A dash BKSF composed with R cap F is the same as the corresponding extensional hull of A dash being BKSF composed with R F cap. So you see here the role that was being played by the T norm, left continuous T norm that gave rise to the residual lattice. A similar role is played by the product T norm here with respect to the F implication. Finally, what about monotonicity? If you use BKSF composition inference scheme, will it have monotonicity? Well, notice it that when we discuss monotonicity, we already started generalizing from the class of R implications to implications, fuzzy implication which satisfied both OP and NP. So we were able to show that anybody that fell here is in the intersection of NP and OP. We were able to show that incorporating them in the BKS inference scheme, instead of IT taking that implication high, having both OP and NP, we were able to ensure monotonicity. We also mentioned that similar result is available when we considered implications which are both strict and satisfying neutrality property. They can also be shown to have monotonicity when employed in the BKS inference mechanism. Now quickly recall, by I if we denote a set of a fuzzy implication, By I and P we denote set of a neutral implication, and a strict fuzzy implication is one such that it is strictly monotonic everywhere except on the left and top boundaries. That means when x is equal to 0 or y is equal to 1. Clearly from the formula we see that all f implications are strict implications. They are constant only on x is equal to 0, y is equal to 1. If you consider the set of all g implications, not all of them are strict. For example, we do know that the Gauguin implication is a g implication, but it has OP, it is not a strict fuzzy implication. However, there are many g implications which are in fact strict and satisfy NP. For example, the Reichenbach implication. So we see that since IF is contained in this and IG intersects with this set, and any implication coming from this set does enjoy monotonicity when employed with BKS inference, we see that when you use F implications or G implications from this set, they continue to enjoy monotonicity. Let's recall the main result. So we are given a strictly monotone rule base. That means the antecedents are ordered in one fashion and the corresponding consequences are ordered in the same fashion, and we are using the alpha cut based ordering here. And we consider the special class of fuzzy sets, f star of x, where if A belongs there, it is a normal, convex, continuous fuzzy set which is strictly monotone on both sides of the kernel. If you construct the partition Px and Py from this class of fuzzy sets, and if these the antecedents which are part of Px, if they form Ruspini partition on X and the consequence form a Ruspini partition on Y, we have a strictly monotone rule base, and T is any T norm and I is equal to IF. Then it can be shown the system function G of the FRA system where we use IF instead of IT is also monotonic. A similar result can be proven also for G implications which are both strict and satisfying NP. A quick recap of what we have seen in this lecture. We looked at BKSF with F implications, essentially considering IF instead of IT, and what we are able to show is that all the desirable properties of a BKS that you could have with I being a residual implication obtained from left continuous T norm, these properties are also available for BKS when you consider substituting I with an F implication. Clearly, such results also hold for G implications. In the next lecture, we will look at some functional inequalities and the corresponding computational aspects, how they impact the computational aspects of a fuzzy inference scheme. Specifically, in the next lecture, we will pick up the functional equality, the law of importation, and see how it allows us to modify CRI in the case of multiple input rules to obtain a more efficient, computationally more efficient scheme, which is also equivalent to the original scheme that you could have considered. Note that this is the work of Mandal and Jairam, in which they proved monotonicity of an FRA, especially BKS, when you employ a fuzzy implication which is both strict and satisfies neutrality property. And another recent paper from Santhan Mandal on showing the same when the fuzzy implication is not strict but satisfies OP and neutrality. Glad you could join us for this lecture. Hope to see you soon again in the next lecture. Thank you again.